think without further ado, we are ready to begin. Greetings and welcome back to the 2021 Yampa Basin Rendezvous. For those just joining us, welcome to our second panel focusing on the latest drought science. My name is Nathan Stewart. I'm faculty at Colorado Mountain College and a member of the steering committee for YBR. In a moment, I will introduce you to our moderator speaker for this morning's panel. Before I do so, I'll briefly remind you of some of what we've become so familiar with over the last year and a half here under Zoom. Given the meeting format, we're each needing to be diligent of our own muting, so we ask that you pay attention to that. We also strongly encourage you to interact with our speakers here today. Please do so via the chat. We had really lively chat use in our morning session. We encourage you to continue to do that. Put your questions there as they occur to you. No need to hesitate, and we'll handle those in a final Q&A session. If you're interested in miking in and speaking your question, which we also encourage you to do so, use that raise hand function. And our technical team will be watching for those on the side as this panel proceeds here. We have the opportunity to hear from and interact with an exceptional group of scientists here today. I'll show you a quick glimpse of them here before introducing our moderator speaker, Dr. Michael Dettinger. Michael will then introduce our colleagues joining us here today. So with that, it's my pleasure to introduce Michael Dettinger here. We provide a little bit of his bio on the right, but would like to use the chat here at this moment to highlight our broader brochure, which includes Michael's bio in full. Mike is a visiting researcher at the Center for Western Water and Weather Extremes, Scripps Institution of Oceanography. He comes to us from a career at the US Geological Survey. Mike did his PhD at UCLA. His work continues to focus on Western water and climate. Today, he'll speak to current drought conditions. Mike, welcome. It's a pleasure to have you.
Thanks, Nathan. Thanks. Next slide, I suppose. So before I introduce the real panelists, I wanted to just kind of kick in, I suppose, some of my own, some of the things I'm keeping an eye on in terms of the current drought conditions. And this builds to an extent on some of the concepts and facts that Megan and Marty mentioned in the previous panel, but drilled into in slightly different ways and with maybe some slightly different lessons in some cases. Anyway, so last year we had another virtual workshop where we talked a bit about new ways of measuring and presenting measurements that well, basically for a changing climate. And one of the figures I showed at that point was this figure here. And all that's going on here, this is showing the combined storage, water stored in snowpack and in major reservoirs in the upper Colorado River Basin. And the whole idea was, hey, because we're losing snowpack and the like, we really can't treat those two storages separately. We want to start looking at them together. And just to explain for the next slide, what this one is showing, the shaded areas, the gray, the blue, and the white are respectively, the blue is a sum of storage. The normal storage by month of year in this case in 20 reservoirs up above Lake Powell. The gray area is the normal storage, historical storage over in Lake Powell piled on top of, so the sum of the reservoirs above and Lake Powell is the top of the gray area. And then the white area there is the normal snowpack, all in million acre feet here. This is the figure for this year so far, this water year so far. And that's all the normals. And then on top of them are three curves. The green curve is this year's sum of Lake Powell plus 20 upstream reservoirs. The heavy red curve is the sum of the 20 reservoirs. And then the light red curve is the snowpack, the water in snowpack by day of year, again, added with, well, piled on top of, added to the water in those upstream reservoirs. So we're sort of keeping track of everything simultaneously. Way over here in the lower right is a figure that's basically a blow up of what's going on with those 20 upstream reservoirs up in the upper Colorado. And it kind of gets washed out in the bigger figure, but you can see the decline that we're in over the course of this summer as that red curve just dips radically in the recent months. Next slide. So having explained that one to you, I'm going to basically throw 5 of them at you. So I've just joined them end to end over the past 5 years. And one of the things, well, there are a number of things to look at here. There's a mix of years here. In 2017, we had quite a large snowpack. That's why that dashed red curve is going well up above the white shaded area. In 2019, we had a similarly pretty good snow year. Whereas in 2020, we had an almost exactly normal snow year, as shown here. When you pull all these together, there are several lessons. Just one is that if you look at 2017 and 2019 and what happened in the next year after those, one thing that you see here is that a single big, well, I should back up and say, basically, you see this long-term decline in the green curve, which is, essentially all the reservoir storage of Powell plus these 20 representative upstream reservoirs. You can see that long-term decline that both Marty and Megan were talking about. Strung together this way, looking at 2017 and 2019, you can see that a wet year with big snow year can turn that trend around pretty quickly, make a big dent in it. But if you look at 2018, 2020, the subsequent years, it doesn't last for long. If we're in another dry year or even a normal year, 2020, the decline begins again immediately. And so a single big snow year can turn a longer term drought declines around, but really only temporarily, unless it's going to take a string of very wet years to break this drought in any meaningful way. And then the 2020 sort of also shows us that's the one that's nearly normal snowpack and the like. And yet, if you look at the green curve there, boy, the drought continues the water levels, the storage in Lake Powell and the upstream reservoirs continues its decline. So at this point, a single near normal year isn't going to actually interrupt the long-term drought declines. So looking forward, if it's another drought year, well, it's another drought year. If it's a normal year, the reservoirs are going to act as though it's frankly a continuation of the drought. Only a big year is going to break us out of this thing. Next slide. Like I say, I'm just showing you some other ways of looking at the data and other lessons perhaps to be taken from it. What we've got here are 2 maps that show the precipitation deficits on the left and streamflow deficits on the right. And they're both on the same color bar, and it's a weird color bar in that instead of showing you, I don't know, inches or percents or standard deviations or something like that, these are scaled basically to show the number of missing water years worth of either precipitation on the left or streamflow on the right over the last 2 years, 2 water years since October of 2019. And I'll just summarize down there at the bottom, just for time, on average over that 2-year period, precipitation is about half a normal year's precipitation behind, okay? So that's how, that's a different way of measuring the drought, but that's where we're at in terms of precipitation. And by comparison, those stream flows, and these are all stream gauges where we're looking at natural unmanaged stream flow. The stream flow is well, as it says there, about 0.8 years behind. So we get this sort of amplification of the drought as we go down from what falls out of the sky to what shows up in the streams to what shows up on in our reservoirs and in various uses. Next slide. And part of what's going on there, I'm trying to do quickly, but part of what's going on there is that drought has two faces, and modern drought really has two faces. Okay, this is going to be a theme that will recur through all the presentations in this panel going forward. And I just wanted to make a simple point about this. Typically, we often think about drought as a lack of precipitation. These days, because of the sort of warming effects and greater evaporative demands that Megan was referring to in her presentation, that contributes to. And so as it says here, if the precipitation for a given area, given year is below normal by some amount dP, but the evaporative demand is normal, then one of the ways we define this is in terms of keeping a well-watered lawn well-watered. That would require an extra amount of water equal to dP, okay? And that's the way we often have historically attended to droughts. But really, there's another way we get droughts, and that's if evaporative demand is above normal, but the precipitation is normal, then we would need to, in order to keep things all well watered, we would require an extra amount equal to that evaporative demand surplus. Okay. And when you have both of these things at work, which is what we're facing now, things get complicated, but fundamentally, you get this multiplication, I suppose, of the drought impact of the drought, of the forcing of the drought. Next slide. And this is a relatively complicated slide, but I just want to, we've been hearing all morning, and you've probably heard over, everywhere, hey, evaporation is a big deal now. I just wanted to put some numbers to it. Okay, so you can know how big. Is this a small influence adding on to the drought? Is it a big influence going on there? So, okay, so we've got three maps here. On the left, we have a map of the net precip deficits over the last 2 water years. Last time I showed you this, it was in terms of missing years of water. But now I'm showing it to you, color bar there is in terms of millimeters of missing precipitation. I could have used inches, I could have used feet, okay? And why I say that will become clear in a moment. In the middle there is the corresponding map of net evaporative demand surpluses. Again, and for both of these, I can look at them in terms of feet of either too much evaporative demand or too little precipitation. And I can start adding that up over the whole area, and that funny looking rectangular thing, there's my very simple-minded version here of the upper Colorado River. But upshot is I can start to add up millions of acre feet worth of precipitation that are missing, or evaporative demand that's excessive relative to the long-term normals. When I do that, for those two maps, basically in the upper Colorado for the last 2 years, the total volume of evaporative demand surplus comes to a number of million acre feet that is equal to 86% of the corresponding total precipitation deficit in million acre feet. So this, if you want to know if these evaporative demand increases are a small correction or a big deal, they're approaching as big a deal as the precipitation deficits that we've been experiencing over the last couple of years. On the right there is a map where I take, and here's where it gets a little bit funky, but I take the precipitation deficits, that leftmost map, and add it to the evaporative demand surpluses, the middle map, and I call that the total drought forcing. And there's a lot of issues with me saying that, but that's a metric of the total drought forcing. And then I ask how much of that total drought forcing is from the net precipitation deficits. And so this map is where the reds on this rightmost map are where the precipitation deficit is the big driver. It's the big number. The green on this map is where the evaporative demand is actually a bigger contribution towards drought than the precipitation deficits, okay? And then the whites are where they're roughly equal amounts, okay? Now, if I take again our funky looking rectangular upper Colorado River Basin and just ask area-wise, how much of that area is either in greens or whites. So it's in area, the evaporative demand surpluses values are larger or nearly equal to the precipitation deficits. What I find is that 63% of that upper Colorado River Basin is dominated or by the evaporative demands, or actually they're roughly equal. The evaporative demand is contributing roughly equal to the precipitation deficits. So, in terms of how big is this thing that we're going to be ranting about all panel long, it's a big deal in the current drought. And it was a big deal in the earlier parts of this drought. And it's going to get it be an even bigger deal as we move forward in the climate changing world. Next slide. So just to reiterate real quickly, you've seen the general decline in the reservoir storage over the past few years. Lesson number one, a single very wet year can turn things around, but it's only a brief turnaround. On average, what right now we're seeing is that the precipitation has fallen behind by about half a normal year, whereas the stream flow is rapidly coming up on maybe a year behind normal over just the past 2 years. And finally, those evaporative demand surpluses have added to the current drought in amounts that are, by any metric, well, maybe not by any metric, by my metrics, is very comparable to the precipitation deficit part of this drought. Now, these are weird ways of looking at it. This is not your typical ways of looking at the drought. And so I encourage you to think about going to the drought.gov site and looking into going through there are portals to just about any way you can imagine representing and tracking the current drought, especially if you dig down towards the intermontane west parts of those menus and the like. So next slide. I'm sorry I had to race through that, but that's the deal. So the real panel starts now, and we're going to have Ben Linda is going to begin. Angie Pendergrass will do the second bit, and Chris Milley will wrap up before we get into questions and answers. Next slide. So I wanted to just go through up front and introduce my colleagues here. So Ben will be starting us out, and Ben is an assistant professor at Ceres and CU Boulder. So he's got his Colorado credibility there. He got his PhD from University of Washington and worked there for a bit. His primary research themes are impacts of changing land cover and climate on water resources. And today he's going to be focused mostly on snow drought. I should say there's more detail in the panel, in the flyer that has been linked to several times over in the chat. And in the interest of time, next slide. Following Ben will be Angie Pendergrass, who is an assistant professor at Cornell. She's also a project scientist at NCAR. So she's got her Colorado cred, and her PhD was also from UC, but all these UCs flying around, University of Washington. Her primary research themes are intensity, spatial, and temporal distributions of extreme precipitation. But today, because we're talking drought science, she's going to talk about some of her work on flash droughts and what that is and how it links into what I've been ranting about for the last few minutes will become clear as soon as she starts talking about it. Next slide. And then finally, we'll wrap up with Chris Milley, an old friend of mine. I knew him back back when he was studying for his PhD, and I was studying for my master's back at MIT, way back in the day. He's a research hydrologist, a senior scientist for the USGS, and he's a longtime research affiliate and resident of NOAA's Geophysical Fluid Dynamics Lab at Princeton. His PhD was from MIT in 1982. His research themes are global hydrology, climate, and global climate, and continental water and energy balances. And his particular Colorado cred comes, if nothing else, from the fact that he is one of the absolute leading experts on climate change and the upper Colorado River Basin. He has revolutionized the way we look at it in many ways, and he'll be talking about that today. So I believe the next slide might lead us into Ben's talk. Is that right? Yes. So take it, Ben.
Thanks so much, Mike, and thanks to the organizers and everybody for signing in today. Yeah, so before I get started, I just want to acknowledge some of the contributions to this talk from Andrew Badger, Aaron Heldmeyer, Nels Bjarke, and Parth Modi. Next slide, please. Yeah, and I hope you guys can hear me okay. I'm having some Wi-Fi issues. Hopefully those won't come into play. So yeah, Mike did a nice job of introducing the concept of drought. And I wanted to talk a little bit about snow drought and some new work that we've been doing on this. So in general, snow drought is a condition of low snowpack, and that has obvious implications for water management and a wide range of other things. This concept of snow drought is not necessarily a new concept, but in the past 5 or 10 years, there's been a lot more interest in it. And in particular, this recent study by Harpold et al., on which Mike is actually a co-author, that was sort of the first paper in a long time to really make some clear definitions. And I just want to propose or define these. So there's this idea of a dry snow drought, which kind of sounds funny to have a dry drought, but essentially that's just a lack of wintertime precipitation as defined by Harpold. And then there's this idea of a warm snow drought, which I think is quite interesting, especially in the context of a warming climate. So what's interesting about the warm snow drought is that you have essentially near normal or even above normal precipitation, and yet you have a lack of snow accumulating. So it's really the effect of temperature. So I'm just going to hit on some of the high points here, and we can move to the next slide. Yeah, so thinking about how these droughts all connect to one another. So at the top, you see meteorological drought, and that's kind of akin to some of the things that we just heard about. So low precipitation, high temperatures, high evaporative demand. And then at the right, you have hydrologic drought, which is what we would think about when there's low stream flow. And that's important because that's what flows into our reservoirs. So the place that snow drought fits into this is off to the left there. And so you have low snowpack, and that's connected to meteorological drought given reduced snowfall. And even, there's a lot more interest more recently on rain on snow events. And then snow drought connects back to hydrologic drought through snowmelt, either the total magnitude of it, the timing of it, and that we know is really an important input into our reservoirs. Next slide, please. Okay. So here in the work that we did, we kind of want to extend what Harpold et al. Did and propose essentially 3 categories. So we propose, oh, I hope you guys can hear me. I've got a internet unstable warning. My apologies. Okay, I'll just keep going. We propose a dry, a warm, and then this combined warm and dry snow drought. So I'll kind of walk you through how this works, but we looked at the upper Colorado River Basin, which is the map on the left, and we used a combination of observations and models. And we used this technique called clustering to produce this graph on the upper right. And it's done based on the ratio of snow water equivalent, which is SWE over P. So that's that vertical axis. And in the horizontal axis, there's the cumulative precipitation. So I've got those red arrows there. And what they show you is that, for example, these warm snow droughts, they occur when precipitation is at or above normal. And that's, I think, quite interesting. Then you have the other 2 types of snow drought, the dry, which is blue, and the purple, which is kind of a combination of both. And the purple type is the most severe, is what we're finding. So next slide, please. All right, so all I'm showing you here is just the history of the last 100 or so years of snow droughts in the upper Colorado River Basin. And I've got them colored, the years, based on which type of snow drought they were. And I've got that little arrow there at the bottom, which shows you that, yeah, you can have these warm snow droughts, which means you actually have around normal or above normal rainfall, and yet you have a deficit in stream flow. And I think that's really important to consider, that because snow is such an important reservoir and such an efficient reservoir for converting precipitation into stream flow, when you don't have enough snow, you actually have a situation where you can have less than normal stream flow. If you can advance to the next slide, please. Okay. Next slide, please. Thank you. Sorry, I apologize for the internet. I was going to try to turn off my camera, actually, that might help. So one of the things to consider, one of the things to consider is that snow drought expresses itself along elevational gradients in really important ways. So what I've got on the lower right is what's called sort of a hypsometric curve, where you see the amount of land at different areas or at different elevations. Yeah. And so you can kind of see that we have a lot of land down low, and as you go up, you get less and less land. Then we can look at the amount of snow, or actually the anomaly. So how different the snowpack is compared to normal in terms of during snow droughts. And what's interesting is that sort of first, I guess, orangish curve, which is the warm snow drought, primarily affects snow at low elevations. And that's important because those lower elevations are places where, the snow probably would be melting first. It's also where most of the land is. And so changes in snowpack at low elevations is sort of the characteristic of a warm snow drought. The dry snow drought, which is the blue or purple, is where you kind of have this more uniform decline in snow. And that's largely because the way we're defining it, which means it's an overall reduction in precipitation. And then the last type of snow drought, which is on the left, that is kind of a combination of the two. And that's where you actually see the largest deficits in snow altogether. So if we can go to the next slide, please. Yeah, and we wanted to basically subset years, the stream flow, the stream discharge based on these drought years. And what we found is that this is for the entire upper Colorado River Basin, but actually we also did this for the Yampa and other basins where the Bureau of Reclamation provides stream flow, is that, yeah, all of the snow drought years show declines in total flow, But what's interesting is the timing of the median, or when the time at which you get half of the flow happens earlier for the warm and for the dry case, and for the combined case, it happens as much as 2 weeks earlier on average. And so thinking about planning for and storing the snowmelt, this is an important consideration. Okay, so next slide, please. Yeah, so I want to transition from looking at historical snow drought to looking at what future declines in snowpack might mean for water supply. And in particular, if we're trying to predict seasonal water supply during a drought. Yeah, you can advance there to the next slide. Thanks. Yeah. So our hypothesis here, which I've got illustrated, is that snow will have reduced utility for seasonal water supply prediction under a situation where we have future snow decline. So I've got this image on the left, which is kind of like the current or the historical climate, where you can see those two stations, A and B, that monitor snow and that are, have a decent amount of snowpack on, important dates, like say April 1st. And they have kind of this reliable historical relationship between the snow and the stream flow and kind of what flows into the reservoirs. On the right is the hypothesis for the future, where there's potentially less snow. You can see we have this station B, which has no snow. And what we are hypothesizing is that this will fundamentally alter the relationship between snow and stream flow and our ability to actually capitalize on that relationship. Next slide, please. Okay, so here's an example of how snow is used to predict stream flow. I've actually taken, this is data from the Yampa River near Steamboat Springs, so highly relevant. And on the right, there's a SNOTEL station, which I believe is in the basin, and I'm not remembering the exact SNOTEL location. Nevertheless, you can see from this is a time series of the April 1st snowpack each year, so that's the blue line, and the April through July stream flow or water supply, the black line. And you can really see that those two lines are closely related to each other, and that's why we use snow to predict. That's how we can use snow to predict stream flow. Yes, you can advance this. Yeah, and so typically the way this is done is we would calibrate, say, the red line over maybe a 30-year period. And then in the following 5 years, that calibrated relationship can be used to predict water supply in the green there. And if you advance just one more, we wanted to understand how this works, how this would change as you go out to 2100. And obviously, we don't have observations of snowpack and stream flow out to 2100. So if you advance one more, yeah, we used data from the VIC model, which was this publicly available data set as part of the CMIP5 ensemble. And there was this hydrologically downscaled data set, which consists of close to 30 different realizations of the hydrology. Next slide, please. So what you see here is a map of the change in the sort of predictive skill of drought out to the end of the century. Warmer colors show places where seasonal water supply predictions are perform worse during a drought, and the cooler colors are places where there's no change, or actually the performance gets better. We did this using something called an equitable threat score, which is that little table on the upper right, and it basically says that, yeah, was a drought predicted, yes or no, from that statistical model, and if it was and then was a drought observed? And in our case, we're using the physically based model as a sort of stand-in for that. What was interesting in each of the 4 regions was that the decreases in skill primarily seem to come from missed forecasts. And this is really concerning because this is a case where a drought occurred, but it was not predicted to occur. So if you think about planning and mitigation and preparation, that is one of the most difficult scenarios where you don't anticipate a drought and then it occurs. Next slide, please. Yeah, and what we did too, part of this was motivated by work done with the Western Water Assessment. We had stakeholders who were interested in this work. What we found was that the projected changes in predictive skill were really the worst or the most significant at low elevations. And actually looking at snow information at the highest elevations seemed to be the places where we had the least impact. And so our recommendation was that out to the future to focus on predictive snow information from the highest elevations. Next slide, please. And so far what I showed was just if you used snow alone as a predictor. And we do know that actually snow is not the only predictor that's used. So we made this combined estimate and combined forecast scenario with, I think you can advance one more, there may be a animation there. Oh no, I'm sorry about that. If you wouldn't mind going back. Thanks. Yeah, we added precipitation, we added temperature, and we also added soil moisture, which is a little bit more experimental. And what we found was you can really use, you can gain a lot by adding those, especially at the sort of lower elevations where snow is expected to be most impacted by warming. Okay, next slide, please. So the last thing I wanted to touch on was this new work we're doing where we're trying to study historical drought events and trying to see what can we learn, what can we gain from this to improve or make us more resilient to droughts and predicting them. So I'm just showing you a map here of something like 32 stream flow gauges from the USGS and about twice as many SNOTEL sites. Yeah, you can advance the slide. Thanks. And so kind of this is a big summary, but we tried to look at ways in which if you could somehow anticipate that a drought was in progress, could you improve your forecast? And sometimes forecasts are issued as early as January 1st. So this horizontal axis at the bottom, that's the date that the forecast is issued. And then the vertical axis is the kind of the error in the forecast. So you want to be closer to the bottom of the graph. And when we did train our models on drought years exclusively, we found that we were really able to improve our drought forecasts even at longer lead times. And even though the skill improves throughout the season, that the biggest gains happen when you have some knowledge that a drought is currently in progress. And what we're experimenting with now is this sort of adaptive sampling. So if you're in a drought, you train your prediction model on historical drought years. And that can be something as easy as saying, okay, it's January 1st, our snowpack is well below normal. Let's go and select some historical years that are well below normal to use for our prediction. Next slide, please. Yeah, so to summarize, snow drought in the upper Colorado River Basin can be meaningfully distinguished as being dominated by warm and or dry conditions, and they play out really in unique ways along elevation gradients. For water supply prediction, our sort of recommendation was predictions should try to focus on using higher elevation snow information in the face of warming, and that alternative predictors may be useful at lower or transitional elevations. And then the last part was this idea of adaptively forecasting, using historical drought years as another potential avenue. Next slide, please. So I want to acknowledge funding, and I also want to let everybody know that we're currently working on this project where we are trying to identify alternatives to snow-based streamflow predictions. And we're conducting a survey where we hope to incorporate what we learned from the community in terms of the methods or data sets into our analysis. So if you're interested, please send me an email and we'll add you to that. And we're going to have a workshop in about 1.5 years as well that you would be invited to. So I think the next slide is my last slide. So thank you very much for your time. And yeah, thanks very much.
So Nathan, I'm not sure what you think. The way we had talked about doing this is if there are, very much clarifying questions, we can, one or two, we might be able to address them right now, but otherwise, for questions for broad comment or opinions or that sort of thing, let's hold them off until the Q&A session. So does anyone need any specific information to understand what you've been hearing from Ben? Okay, that was a very clear presentation, so that's good. Let's push on. Let's get through our presentations and then we'll have a conversation. So next slide. So as I said, next up is Angie Pendergrass. Next slide, and she'll be talking to us about flash drought, just as I said. So have at it, Angie.
Hi, everyone. Thanks so much for having me. It's pretty exciting, even though we're on Zoom, so it's not as cool as actually coming to Steamboat and maybe going tubing in the Yampa, which I know is really fun. So I am going to talk to you about flash drought, which is something that I coordinated a workshop and then a paper about. The workshop was in, I think, 2018, definitely the before times, with AGCI. I noticed there are a couple of people from AGCI on the call who were know about that. So there's a lot of people that were involved in this, but I'm not going to go through all of them right now. Okay, next slide, please. So I want to start out by telling you about the flash drought event that kind of got flash drought on the radar of the media. Now, flash drought is a concept that was named in a paper in 2002 by Mark Svoboda. But this 2012 event really brought it to the forefront of a lot of people's minds. So what happened here was early in summer, in June, if you look in this box in the top panel, you can see that looking at the US drought monitor, there was very little drought in the central US. And then over the course of the next month, so just 1 month, just 4 weeks, that went from very little drought to lots of extreme drought and some exceptional drought. So these D3 and D4 categories from the US drought monitor. And so what's so remarkable about this is how quickly this drought onset occurred and how rapidly it intensified. And what that ended up leading to was a very low yield of crops for that season. And so this was impactful for agriculture. It was impactful in terms of dollars. And so it got a lot of people's attention. Now go to the next slide, kind of. Yes, this one. As Mike generously introduced already, one of the factors that we think is important with flash drought, with these particularly rapid and quickly intensifying drought events, is a higher evaporative demand than normal. And so what I'm showing here in this kind of middle column is the evaporative demand drought index. And so that's something that Mike Hobbins put together. And what that shows is that there was a really large increase in evaporative demand that preceded this flash drought. It preceded these the increase in the drought indices according to the drought monitor. Now, this is something that's important and useful to do, to come up with these kind of physically based metrics for flash drought and for drought, because the US drought monitor is not quite a physically based product. What that is it's got some inputs, including a lot of observations, but it also involves a whole lot of human effort. It involves people on the ground all over the country, the US specifically, getting together every week and discussing what the status of what's happening on the ground is. And so that's something it's very valuable, but it's not necessarily predictive. And also the way that that system works has a lot of lags built into it. It was kind of set up with the idea of long-term droughts in mind. So it's not necessarily intended to capture these events as they're unfolding on the timescale of a week or two. What it's really intended for are droughts that are longer term, that are taking place over the course of a season or longer. Okay, so go ahead and go to the next slide. Okay, so I've already told you a little bit about what flash drought is. So there are these droughts that have rapid onset or intensification, specifically on a time scale of 2 to 4 weeks, so less than a month. But 2 weeks is also a kind of minimum threshold. The idea being that if you have dryness lasting less than about 2 weeks, it's probably not necessarily going to have strong impacts, especially not beyond just the precipitation deficits. So it can either be a rapid onset or a rapid intensification. Probably to be the rapid onset, it has to have a rapid intensification, but of course it depends exactly how you define it. And exactly how that should be defined is something that's still an area of active research. And the other characteristic that we think should be included to qualify an event as a flash drought is that it's impactful. It has impacts of some kind, whether those are agricultural impacts, whether they're shipping impacts, you can't drive your boats up the rivers, or what have you. We think it should have some sort of impact. So go ahead and go to the next slide. Oh, okay, so you're gonna have to mentally adjust these maps. You can see that the southeastern US is on the top, and then the northern part of the US is on the bottom. But anyway, what these series of plots are showing are the atmospheric circulation in the 30 days leading up to flash drought events in a study by Ford and Lavoisier in 2017. And so again, this is further east in the US, but what this is showing is that identifying these flash drought events at particular locations, if you look at what the atmospheric circulation was doing leading up to that event, it's got a pretty distinct ridging pattern in this particular analysis. And so the reason that that's useful and interesting are these short-term events are also happening on the timescale where we might actually have predictability in the atmosphere, right? So chaos theory tells us that we lose predictability after about 2 weeks. But these ridging patterns are something that perhaps we could hope to be able to have predictability of. And sometimes these ridging patterns are a little bit more persistent and perhaps a little bit more predictable than flow is in the atmosphere on average. Okay, so go ahead and go to the next slide. It's probably going to have this. No, oh, this one worked. Wonderful. Okay, and the other reason that that flash droughts are something that got people's attention is many of these events are coincident with heat waves. Some definitions of flash drought even actually require there to be a heat wave. And so this ties into this increase in evaporative demand because Clausius-Clapeyron, the saturation vapor pressure holding capacity, if you will, of the air increases exponentially with temperature. So when you have hotter temperatures, you have higher evaporative demand. And so this lays the foundation for potential compounding extreme events. So a flash drought coincident with and on top of a heat wave. And so separate from the dryness, this heat can have its own impacts, and together we might be concerned that those impacts could multiply. Okay, go ahead and go to the next slide. Okay, and so this is a figure developed by Mike Hobbins that lays out some of the physics that have been hypothesized to make flash drought a little bit special compared to longer timescale droughts. So what this is showing is time on the x-axis and evaporation and evaporative demand. That evaporative demand is E0 on the y-axis. And so when you have, what the idea is if you start out in a wet regime where you have a lot of soil moisture and you're in an energy limited state, then as you have increases in evaporative demand, you'll have increases in evapotranspiration. But then if you get to a point that the soil has dried out, so it becomes moisture limited instead of energy limited, then you can actually end up having a change in your regime of land surface interactions with the atmosphere. And you can actually then decrease evapotranspiration. So the idea here is that if you start out in a wet regime, you can find yourself thinking everything's okay until you get to this point where you transition from the energy limited regime to the moisture limited regime, in which case you very quickly can find yourself in a drought that rapidly intensifies. So that's like the canonical way of thinking about a flash drought event and how it can intensify so much more rapidly than one might expect if one was not paying attention to this particular set of transitions. Okay, so now go ahead to the next slide. Okay, and then of course we can take a step back and acknowledge that precipitation deficit is often usually a contributor that's important for all kinds of drought, including flash drought. So here we can see just a kind of relatively simple plot showing deficits of precipitation, which then led to drought. So we don't want to forget that. That's very important. And it also places some challenges because predicting precipitation is much harder than predicting things like temperature or atmospheric circulation patterns. And so when we get into this regime where precipitation deficits are driving our droughts, that's going to decrease our ability to predict them. Okay, so go ahead, next slide. Okay, so for flash drought monitoring and prediction, some of the things that are special challenges and opportunities compared to longer timescale droughts that have their onset kind of more slowly evolving is first of all, this issue that drought monitors have mostly been designed to detect longer term droughts. So if we need to start paying special attention to what's happening on these shorter timescales, if we want to be able just to know what's happening now, are we already in a flash drought? Is something going to happen over the course of the next week or two? And has it already happened actually in the last week? And we're still catching up in terms of the impact. So these are things that with improvements in monitoring and focusing on this a little bit more, we might actually just be able to improve things that way alone. And then the other thing that was a little bit exciting for us about this, why we wanted to go after this, is because there's been a lot of energy in the last few years in atmospheric science about improving predictability on the sub-seasonal to seasonal timescale. So this window that's a little bit longer than where we're usually doing weather forecasts, but that's still potentially short enough that we might be able to learn some information. And so the idea here is that perhaps we could think of flash droughts as a target, right? They have impacts that we want to try to mitigate if we can find out about them as early as possible and tell people so that they can take action to prevent impacts that haven't yet unfolded but could unfold. And so the idea there is that there might be some potential for early warning if we try and focus on that. Okay, so now go ahead to the next slide. Okay, what about the Upper Colorado River and the Yampa basins? That's what this meeting is about. And so what I'm showing you here, which on my screen, I can't really see the reds, but what this is showing is the entire time series of the US Drought Monitor up through 2016 or so, when this paper from Mike Hobbins was published, over the Upper Colorado Basin on this bottom axis here. And then the upper two axes are showing basin mean eddy evaporative demand drought index for the Upper Colorado River Basin. And so what's different about the Upper Colorado and the Yampa than these other regions where flash drought has largely been studied is that it's a net arid basin. It's net evaporative. So it's normal to already be in this moisture limited state. And this region is rarely starting out in this energy limited state where there's enough moisture. And so it's much less likely that you would find yourself going from this quick transition from the energy limited regime to the moisture limited regime. And so it's unclear at the moment what that means for flash drought in the region. Does that mean that there aren't flash droughts? Does that mean that these flash droughts have a different mechanism? Because it's still a little bit early days in thinking about what it is that flash drought is and how we should define it and what we want it to mean. It's still yet to be determined and defined. So the other reason that this is important is because we know the climate is changing and we know that evaporative demand is increasing, as Mike has already alluded to. And so it's a really important question to ask what that means. And so it's pretty difficult to untangle these things. And in the time since I've published this paper that we worked on, and now there have been a few people chomping at the bit, starting to ask these questions about how might flash drought change in response to warming, what happens in model simulations. It's still a little bit unclear, right? So climate change is generally about mean state, and it's much harder to get at what this means for an anomaly relative to a changing baseline. So these are all still open questions. This is an interesting area to work on, and I probably have asked more questions than I've answered in this presentation, but I think that the topic was supposed to be current science. So I think that that is hopefully okay. So I think that that was my last slide.
Angie, this is Nathan miking in. We're doing well on time here. If you would like me to bring up your 2 additional slides, I'm happy to do that, or we can hold those as well.
Well, let's see, why don't you go to the last of the extras, the second of the extra slides. Yes, this one. Okay, so this is related to and slightly different from what I've been talking about so far. So one of the reasons that we suspect that there could be changes in drought in general and flash drought in particular in response to warming is because overall we see an increase in the variability of precipitation in response to warming. Okay, so when we are talking about things like heat waves, extremes of climate that are focused just around temperature, this is a relatively easy problem when we're thinking about climate change, in the sense that the overall width of the distribution of temperature doesn't change too much in response to warming. So temperature is a roughly Gaussian quantity. And what happens in response to global warming is we take our Gaussian distribution and we just shift it to higher temperatures. And so if you're worried about how often temperature exceeds a particular threshold, all you have to do, to first order at least, is worry about that moving peak of the whole distribution. And that is not at all the case with precipitation. With precipitation, because it's highly non-Gaussian, if we can have, let's see, we have a peak of the distribution, and then that shifts to higher average quantities with warming. But as it shifts to higher average quantities, the tail of that distribution also gets wider. And this has been looked at in terms of the coefficient of variation, so the variability of precipitation divided by its mean, for quite a long time. But the thing that was interesting that I showed in this study is that the variability of precipitation increases even a little bit faster than that. And so that means different things on different time scales and different space scales. The way that that projects varies. But this is something that we need to concern ourselves with. And this is kind of the foundation of why we think that drought might change beyond just the change in aridity, but also the change in drought in response to warming. Okay, and so that's, I've already brought us out another level, but I think that that's an important aspect of the response of drought to climate also.
Thank you, Angie. Same rule as before. Do we have any clarifying questions? So sort of, you know, boy, I don't understand what something was said unless I ask this question right now, leaving our discussion questions until later.
Mike, perhaps I could voice on behalf of Julie Vano one here. I can read it, Angie, for your consideration. What are ways to track that energy to moisture limited regime transition?
Yeah, I think that's a great question. And I think that my expertise is on precipitation. And I think that others here might actually know better than me how you would do that. Can I do that? Can I turn it around to everyone else and make it a discussion?
Please do, Ben, if you feel like you might want to jump in, or Chris, even ahead of yourself, or Mike, feel free to handle that here. We'll keep that as a sort of technical question maybe to address, and then we'll move on.
Well, I'll jump in, this is Mike, and just say that we touched on it briefly, I guess it was in the previous panel, but a question came up about soil moisture information. And I think that, one of the characteristics that distinguishes between a moisture limited and energy limited landscape out here in the West would be trackable, or at least you would see signs of that kind of difference in the soil moisture and in the vegetation moisture for that matter, but in the soil moisture. And honestly, we really just don't have the data, as much data about that as we probably need out here. So, it's not, if I was to push for something to really try and keep a handle on that observationally, I would be inclined to say, boy, let's make sure we've got the soil moisture data collected and coming in. A lot more is being collected these days because it's technologically gotten a lot easier, but it's not necessarily aggregating in ways that we see, in places where we now see that data. So anyway, that's my pitch on that.
I agree. And I think also in order to kind of get at all of those aspects, you also want to know what the energy fluxes are at the ground surface. And that's also something that's difficult to do. You can kind of make inferences about it, but directly measuring it is quite challenging. You got to have a lot of instruments, and it varies a lot in space and in time. So these are difficult things to solve.
Excellent. Mike, perhaps I could suggest that we move on. Angie, you're welcome.
Yeah, no, okay. Well, maybe we'll come back to this during the Q&A. So next up is Chris. And basically take it, Chris.
Okay, here I am. Yeah, so this has been great. I've gotten a lot out of all three of those talks. So, we're in this in-between place where we're talking about drought and we're talking about climate change, and it's not clear always how they separate from each other. Drought, I think of as being a dry departure from normal conditions, and then what is normal, and that the normal is changing as the climate shifts. So I'm going to be talking a bit more about climate change, sort of longer timescales here, and how that affects, I'll say, drying or aridification rather than drought. I mean, if you use as your baseline for definition of drought history, then aridification equals drought. Anyway, let's go to the next slide. So the warming part of climate change, we're not going to talk much about precipitation, especially in the UCRB. It's very uncertain. We're going to focus on the warming aspect. And, we've known about this phenomenon here for a while with warming in a snow-dominated system. There's a shift in the hydrograph, in the average hydrograph. And one of the consequences of that is a hydrological drought in the summer, where the snowpack, that reservoir is now smaller, and therefore the flows are coming out earlier, as has been discussed. One click, please. And in fact, Mike is probably on papers in everybody's presentation here, but this goes back to this sort of landmark paper, Iris Stewart and Dan Kahan and Mike, showing, that the data show very clearly a trend toward earlier timing in the stream flow. So that's one aspect of how warming affects drying and or drought. Next slide. And I want to talk about another pathway. So there's these two pathways. Click once. And we've just talked about how warming affects runoff timing. Click again. And drought or aridification, whatever you want to call it. But then the other route is what I'm going to talk about a little. Click once more. And that is that not only can warming affect the timing of the runoff, but even with no change in precipitation, there is an effect on the runoff volume. There's a reduction in the runoff volume. And that's what we want to talk about here. Next slide. And okay, you've probably seen these pictures. These are annual time series, water year time series for the Upper Colorado River Basin. And you know, for the basin average precipitation, a slight increase over the century, significant increase in temperature, and a significant decrease in the naturalized discharge. And a 0.8% increase in precipitation by sort of normal rule of thumb should give you about a 2% increase in discharge, but we're down 20%. So there's a 22% discrepancy to be accounted for. And if you want to just go and blame that on the temperature rise, that amounts to a 15% per degree C sensitivity of the discharge. And we're going to talk about that sensitivity a little bit here. Of course, things aren't this simple because spatial and temporal distribution matter a lot. Next slide. Just, you know, elementary thing here to help think about the situation where precipitation isn't necessarily changing, but you get a change in river flow due to a change in evaporation, which is basically your income tax. If you think of the precipitation as your gross income, and then the river flow as a take-home pay, what's left after the tax is extracted. Tax rate for the Upper Colorado, I know it's like 90% or something, gross tax. Next. So that means that a small change in evaporation, of course, can cause a relatively large relative change in runoff. So these are actually based on data from a model that we introduced in a paper. These bar graphs, each bar represents a 5-year average, and this is the century history of the Upper Colorado River Basin. As opposed to what I showed you in the previous slide, notice I've got high elevation precipitation here. And this is why it matters where the precipitation changes are. In fact, the high elevation is where the runoff is produced. And it happens that whereas the basin total precip increased over the century, the high elevation precip went down. So, you know, this picture kind of makes sense intuitively, right? So temperature increases evaporation, which decreases river flow. Decreasing precipitation decreases river flow. And what Mike has talked about, everybody's talked about how both of these factors are really quite significant. And in the analysis we did, if you look at the century-long decline in the discharge on the Colorado, it seems that about half of that can be attributed to the warming and half to changes in space-time of precipitation. But what I think is a really interesting question here is that top arrow going from temperature to water loss to evaporation. I mean, it's an intuitive thing, and yeah, Angie has properly introduced the Clausius-Clapeyron relation, but there's a lot of subtleties in there, and it's not immediately obvious why in one location you kind of try to compute this sensitivity and you get a much different number than you do in another location. Or if you try to do some theoretical analysis, you get yet a different number. So that's what this paper that we did on the Colorado was investigating. And one more click. The other part of this, of course, is what is driving the temperature and precipitation changes. To what extent is one or the other of those climate change, and to what extent is it natural variability? So these are these red questions here are kind of things that I think are pretty interesting. Next slide. Oh yeah, so you'll hear this word attribution. For those that aren't familiar, I mean, people talk about detection and attribution of climate change or of the impacts of climate change. So the question here is, to what extent can we attribute changes in precipitation and temperature to anthropogenic climate change? Without getting rigorous, it seems to me that the temperature increase is pretty convincingly tied to climate change, whereas the precipitation in this particular region, the judgment is not so clear. And for this reason, there's been a lot of focus on the upper loop here, because everybody's throwing their hands up at, well, we don't know what's going on with precipitation. It depends on the monsoon and where the what do you call them, the storm tracks and such. And then there's very complicated topography that really complicates things there. So next slide. Just as I mentioned, empirically, we know warmer conditions lead to more evaporation, but to understand that and to be able to use that to make predictions, we have to understand the causality of that. And we have to understand it pretty well rather than just qualitatively. Next. So next. Yeah, so we talk about the sensitivity of river discharge to temperature. I call it beta. So beta is the percentage reduction in flow for a 1 degree, let's say, uniform space-time warming of the atmosphere. Is it 2%? Is it 15%, as I suggested by a simple analysis of that earlier set of 3 time series? Yeah, next, click one more. For the upper Colorado, people have been looking at this for quite a while, and there's been a great range, as I'll show you in the next slide. But aside from being very uncertain, that is the actual magnitude of beta, the sign of beta is pretty clear. It is negative. Warming decreases runoff. Next. So this is, there was this conference workshop held out in Boulder a couple of years ago now, and you got some heavy hitters here that showed up, and there was a survey given. The point of the workshop was to try to narrow, or at least one of the points was to try to narrow the uncertainty in the range of what value beta takes for the upper Colorado. And this is this bar graph, the numbers, I hope you can see, they range from 0 at the bottom to 16 at the top. Those are beta values in percent. And each bar represents one participant at the workshop's estimate of, the range that they think beta falls within. And nearly everybody except the next to the last one included 6% in the range. So you could call that like a median estimate, but they range from down 2% up to 15%. And I don't remember what I thought at the time. I was just going back and forth daily when I saw different things. And maybe related to that is the fact that at the end of the workshop, they repeated this survey and the graph looked just about like this. We hadn't really figured anything out. So I got kind of intrigued by that. And that got me, that's where I started looking at looking at the Colorado, trying to understand it. Next. And, basically the story that we came out with, which, I think is intuitive to some people all along, is that Snowpack Albedo plays an important role in the situation. So on the right, each one of those panels is for a different elevation band within the UCRB. And they show how albedo depends on SWE. And as SWE gets, it's a log scale for the SWE. As SWE gets larger, the albedo gets larger. And as the range actually depends on elevation. If you go down to those lower elevations where there's not much vegetation, you can see the snow looking down from the sun. And therefore, there's a bigger range in the albedo there. As you go to the middle elevations, there's less range. And then as you go to the really high places above the tree line, you can see that large sensitivity of albedo to SWE again. So anyway, the way this matters is diagrammed on the right, where you have a warming, which number one means you have less snowfall, and number two, you have earlier snow melt. So overall, at any given time of springtime in particular, on any date, you're going to have less snow cover as the years go by, as warming proceeds. And as a result, you're absorbing more radiation. And in the places where this water, this runoff is being produced, actually, it's not so much water limited evaporation as to a large extent energy limited. I mean, there's snow on the ground. That's a, saturation vapor pressure is active right there. And so with that extra radiation, it leads to more evaporation. And then assuming precipitation hasn't changed, all other things being equal, you end up with less runoff coming down the river. Next. Oh, so we actually had a model in this analysis, and these are some time series of basin averages, annual time series, basin averages of several things. The precipitation and temperature, you've seen those plots already. The SWE, the gray shaded areas are, we did this thing where, since we didn't know the model parameters, we did Monte Carlo stuff and chose only the small subset of parameter sets that agreed well with observed or naturalized discharge, at least Ferry. And so that model showed a SWE decreasing over the century. And there are some, those aren't observations there below, they're actual model observation syntheses. That decreases, the albedo decreases, the net radiation increases over that time, and the evapotranspiration, because of the scale I used, you can't really see that upward trend as much. And then there's a downward trend in discharge, which is reproduced by the model. Next. And this is the final slide. The question is, what can we say on the basis of this work about the future for runoff or water availability as produced by the upper Colorado River Basin? And I come back to this picture that I had before. There was the attribution question and the causation question. What we really were looking at was this causation question. What is the relation between temperature and evaporation, and not just numerically, but physically, process-wise? Why? So one click, please. Because to this point, there's still plenty of snowpack in the spring where the action is happening in this area, we can now predict, using this process information, that the sensitivity to warming is going to remain high, since it depends on the presence and ability to disappear of that snowpack. In fact, we ran simulations, and the sensitivity does increase somewhat with each degree of warming. Next. Oh yeah, so we made the standard projections that you do from CMIP5 models. And on the basis of the warming and the information about sensitivity, and by the way, I didn't give you a number, but the beta value that we arrived at was about 9%, of which about 2/3 was attributable to this snow albedo effect. Clausius-Clapeyron, to oversimplify in this case, it gives you about 2% sensitivity. So it's the snow that really matters. So anyway, with no precipitation change, the projections would say 15 to 30% relative to the historical, not relative to the last 20 years, decrease. And if we add in precipitation, which is my last bullet, because of the great uncertainty across the climate models, and we used a subset of CMIP5 models, those that best agreed with the local hydrology there. In that case, the sort of central estimate of change in discharge doesn't change much by adding in precip, but the uncertainty gets much wider. So you could have, according to these climate models and our model's estimate of sensitivity, you could have anywhere from a slight increase of discharge to a 40% decrease by mid-century, which is, a couple of decades away, right? And yeah, that's all. Thanks very much for listening.
I'm going to interject. This is Mike, and just say, when I was introducing Chris, I mentioned that he sort of had revolutionized the way we were thinking about climate change impacts in Upper Colorado. And I'm not sure whether all my colleagues would agree, but I always stick my neck out, and I'll just say that revolution was, we were all tending to think an awful lot, Clausius Clapeyron, about a thirstier atmosphere generally. Chris is the one who really fairly recently brought home to us the albedo, role of albedo in this stuff, and that's really where we hadn't been looking in that corner as much as we probably should have. We'd been over in the other corner at the Clausius Clapeyron sorts of effects. So like I said, just to interject, taking advantage of being the moderator here. Do we have any clarifying questions?
Thanks, Mike. Your check is in the mail.
Yeah. Okay. So I believe we're moving into the question and answer session. And the one thing I'll say is I was reminded that Angie might have to leave a little bit early. So if that's still true, Angie, then maybe we'll look at a couple of the questions that were directed specifically towards you first. Is that okay?
Yeah, that's okay. Yeah, I do have to go teach about Clausius Clapeyron and other things. But I noticed that I answered one of the questions in the chat already, but another question from Rachel Santi, which I thought was interesting and perhaps I could address, is she asked how I would recommend we monitor flash droughts on the ground, and also brought up vegetation. So the first thing I wanted to say is this monitoring of flash droughts. The key thing is that you have to look at shorter timescales. So sometimes the information that's going into the drought monitor is averaged over a week or 2 weeks. And if you want to get at things that are happening on short timescales as they're happening, then you really have to look at shorter timescales. The reason that people don't do that is because there's a trade-off. Then your information is noisier and it's harder to see signals. And so there are always trade-offs. And so that's what's tricky about it. But then the other thing you mentioned is vegetated areas. And I don't know, unfortunately, I couldn't make it earlier today, but the one thing that hasn't come up that I think is a really interesting point about how aridity changes and perhaps how drought changes with warming is exactly this point about vegetation. So when you increase the amount of carbon dioxide in the atmosphere, you change the stomatal conductance of plants. So the plants are trying to breathe in CO2 so they can photosynthesize it and breathe out oxygen. And in the process of doing that, they also are releasing water vapor through their stomata. Anyway, so in response to increasing carbon dioxide concentrations, they can close those a little bit and they actually don't lose as much water, all other things being equal. So a really interesting paper by Abby Swan that came out in 2016 looking at some climate model simulations showed that depending on what you assume in your climate model, you can actually find that that closure of the stomata in plants can actually compensate for the increased evaporation that comes from the increase in evaporative demand. So you can have the increase in evaporative demand and then the decrease in evaporation because plants close their stomata, and that can actually compensate for each other. And so there are a lot of big questions. And then that's something you can, say something about aridity with that, but what does it mean for drought? I don't think we know. So I just wanted to ask more questions.
Yeah, so let me jump on that and actually cross off another question in the list, sort of. And that is, way back on mine, Ty asked a really horrible question. I hate you. But basically, what are the options to counteract these evaporative demand surpluses? And that's a terrible question. It's a lot like asking what are the options for increasing the amount of precipitation we get. It's just, oh my God, what are we supposed to do here? I will just pitch in, that I had two answers to that, and one of them is directly related to what Angie was just mentioning. And the one is, in many ways, we want to reduce that evaporation. And so we want to get a lot of the water into the down underground as best we can, and so I tend to look at that and think of all sorts of options. I believe we need that in order to just sort of actually to deal the little bit we can with those stream flow timing changes that Chris was mentioning. And, my answer to this, it's rather flip, is, okay, we need more beavers. We need artificial beaver structures. We need to spread the water out and get it into the soil in the headwaters areas. Like I say, a little bit flip, but also a little bit crazy. I'm not sure how that would scale. But beyond that, the other one is just one thing that I haven't heard anyone say here, and you wouldn't get away with a meeting like this in California without half a dozen hands going up, and that is the issue of, okay, what if we were to thin the forests and reintroduce fire and all those things? Would that tend to reduce these evaporative demand increases that we're seeing into the future? And the simple fact is, I don't have an answer because I'm still skeptical that we've looked at all the ramifications of that. But it's sort of related to what Angie was just talking about. The vegetation is going to play a key role here, and whether it changes because the climate has changed and everything goes up, or we do something to try and reduce fire effects and or improve the runoff efficiency or the runoff generation from our headwaters. Vegetation is going to be key to this stuff. So, like I say, I want to jump on what Angie was saying, but also tick that other really horrible question off. Do anyone else have any thoughts about, what can we be doing, or what can we be even thinking about doing to respond to this whole evaporative side of the droughts that we've been talking about and climate changes?
I might add, thanks, Mike. So we had a workshop a number of years ago on reservoir evaporation. And yeah, like you were talking about putting the water in the ground. So a lot of the water ends up getting held back by reservoirs, and the reservoirs are at different elevations. So we do have some higher elevation reservoirs. And so we kind of back of the envelope made a calculation that if you did try to, and obviously I don't want to upset the reservoir managers here, but that there is a way to maybe store water a little bit more preferentially at higher elevations. You may be able to limit some of the losses to evaporation, but it's a very tricky problem. And it turns out we don't have too many reservoirs at high elevations because there's not as much sort of drainage area, as much land area up there as well. So it's not super easy, unfortunately.
Anyone else want to wade into this one?
I was just going to throw in a comment on the stomatal closure thing. Yeah, that's been a big sort of point of contention in a number of circles relating to whether drought is as bad as projected when people take climate model outputs and run them through historical empirical relationships, which isn't the best thing to do, and whether they're ignoring that factor. On the other hand, we've been doing modeling, a follow-up actually to the Colorado Basin modeling. We're working on the Delaware, and looking at sort of all the processes driving, you know, all the energy factors. And it's very hard with our model to get a significant suppression of transpiration by CO2. There's like not room for it when you constrain the model with the available data from water and energy observations. This isn't, you know, this is just one data point, but I think, you know, it's a really interesting area for research because it is so uncertain.
Yeah, go for it, Angie.
I have to take off, but I just wrote in the chat that I thought I should mention one thing we could do to mitigate the evaporative demand surplus is to mitigate greenhouse gas emissions. It's kind of the obvious answer.
Well,
Yeah,
yeah,
that was mine too.
Thanks so much, everyone.
yeah, it's been great.
Thanks, Angie. Yeah, maybe we can move to another question because
Right, sure.
this one is pretty nuanced, I think.
Yeah, yeah. Well, I'm going to just pull one out. Just so Jeff Deems basically asked Ben, but it's open to the room. The question basically is how much, well, what is the role of, well, hell, I'll just read it. When you say snow, I think you mean, what you really mean is snow as observed at snowtail stations. How do you think our ability to forecast or predict drought, such as you were talking about, would differ if we had very accurate inventories of snowpack as opposed to the only current index stations? And I wonder why Jeff asked that. But anyway, he's obviously involved with ASO. So go on, just thoughts on that?
Yeah, I would say, you know, we obviously are quite limited in what we can observe in terms of snow based on accessibility and other things. ASO is a really cool new way to see snow. From the stuff that I did, we actually used sort of a modeled approach. So the conclusions about higher elevations being more robust, I think are pretty, actually, I think that's a pretty solid conclusion, just that places that are high have less sort of evaporative demand and they're colder, so they tend to hold snow later and longer. I think region to region, though, you're going to see a lot of these interesting differences, and you know, at the scales of like the ASO and the Snowtel, it will matter, and which specific station you choose to make your forecasts using will matter. So I think there's always an argument to be made for adding to our networks for observation for this reason specifically.
Yeah, I'm going to pitch in there. You mentioned Adrian Harpold towards the beginning of your talk, and he's got some work which I'm blindsiding you because he hasn't published it yet. Blah. But anyway, in which he looked at this question in something probably similar to what you were describing, but he kind of pushed it a little bit further and asked, you know, so if we're losing the snow signal, the snow predictant, you know, a predictor, you know, to an extent, what's the alternatives? And I think you mentioned that you, in your work, you've included soil moisture as one of the kind of additions or alternatives. He kind of looked at it to an extent, almost like an alternative. Should we be transitioning towards using soil moisture as a predictor, you know, as snow's role? And I got to say, a lot of this was done in California, where we're going to lose our snow a lot sooner than you guys are. But I'm just wondering, so alternatives, or where was soil moisture in your scheme, your analysis? Ben? Yeah.
Yes, thanks, Mike. So yeah, I'm familiar with an earlier paper that Adrian did using soil moisture, and we brought it in. We kind of talked about that other scenario as like the kitchen sink. Like, what if you threw everything we've got in?
Yeah.
Yeah, it is tricky because the records are not nearly as long. And the siting is probably not, it wasn't like the SNOTEL stations were cited for particular reasons. And the fact that they also measure soil moisture, I think, is important. I do think it's important, but yeah, I think probably something like these evaporative demand indices are maybe an even more attractive opportunity, simply because they're so much more widely available and observable. But it does seem like bringing in something like soil moisture, it's happening a little bit, and I would say it's definitely the future. So we are actually collecting information from water managers, users of water supply forecasts right now with that survey I mentioned. And so I might, in a year from now, I may have a clearer answer for you as well.
So, yeah, sorry about that. So I realized I was typing without muting, but anyway, so let's push on a little bit, and let me see. I'm looking at Chris's list here, and it doesn't mean we won't come back to you, Ben, so don't relax too much. But let me see. Marty Ralph asks, how might increases in dust on snow affect your beta and projected runoff changes and things like that?
Yeah, dust on snow could contaminate our analysis such that we, aliased it into our estimates of sensitivity, for one thing. We tried, when we did that analysis, we had sort of an extra wildcard factor that we tried to estimate, sort of the changes in radiation due to other unaccounted effects, such as, let's say, changing atmospheric CO2 or dust on snow, or or snow metamorphosis. And we didn't find that number became significant. Now, I wouldn't put much weight on that answer that I've just given. I think that's still a question that's open, and I don't know the answer to it really.
So let me see. There was another Marty one that was broad enough that I thought I should bring it up because it's to virtually anyone. Oh God, maybe I can't find it right now. Maybe not. So bouncing back to Ben, let me see here. Yeah, I think we've touched on both of those to an extent, but if you want to expound further, Ben, what do you think are the observational requirements to support alternatives to snow-based predictions?
Yeah, so it's a great question. And I know there's a lot of sort of very realistic constraints on what we can do with ground-based observations, but there seems to be some interest. I think one of the nice new opportunities is to use remote sensing satellites, simply because, we can see the tops of mountains, although what we're seeing obviously is not particularly clear all the time, but we do have some retrievals up there, which is really valuable. To that point, yeah, I think things like the status of the vegetation can be really useful, near surface, humidity, and kind of like this. What we're seeing a lot of now is fire weather, and with the increase in fire, I think ties into the evaporative demand. So my feeling is that there's a lot of opportunity to link the ground observations we've got with the satellites that have been launched over the past 15 or 20 years. And then in terms of requirements, I know that the USGS has a new initiative I think one of their sites is in the Upper Colorado River Basin. I'm forgetting all the acronyms and details, but I think that type of approach, a concerted effort by an agency like the USGS, would be essential to making these sort of observations as relevant as possible.
Okay, thank you.
Ben, I just wanted to ask you a quick question. You mentioned the satellites. And a lot of running through your talk is this idea that, the water is kind of being in different places now as things change, and therefore this predictability kind of gets a little messed up. Total mass from GRACE or GRACE follow-on, I mean, is the spatial resolution just not fine enough to use that in predicting flow?
Can you say that last part again? I'm sorry, I just lost.
Is the spatial resolution of GRACE just
Oh, Grace.
inadequate to be able to make a total mass measurement from which you could make a prediction?
So I think Grace is, what's interesting about Grace, yeah, it's super coarse. It's kind of at the resolution of droughts as we know them, certainly these continental scale droughts. And so like in Angie's talk, she talked about, the Midwest, the drought in the Midwest, and there's that big bullseye on like the US drought monitor. So I think to that extent, and we've done a little bit of work comparing sort of models to Grace at those scales. I think when we get into the mountains, it gets a lot more complicated, obviously, because there's just the length scale of the variability is so short. And so, yeah, we've been looking at, satellites that see snow and the date that the snow disappears. And there's actually quite a bit of information, I think, contained in that could be used. There's been efforts, I think, to downscale Grace a little bit. I'm not so sure, how those are faring. It's attractive though, especially for more continental sort of interior scale, interior type droughts where there's less spatial variability.
Yeah, and I do agree with your assessment of the visible stuff. I mean, that was key to the analysis that we did, just being able to see that snow.
Okay, Guy. Nathan, how much time do you need at the end? We're coming up on the end.
Like we're doing well. Let's entertain another question or two here, and I can just grab those last couple minutes, just cognizant that people might have planned for 12:45 Mountain Standard. Just do a couple.
Okay, so I have two more questions. Hopefully we'll get to both of them. One is a little bit out of, well, it's something none of us have mentioned, and I'm curious whether you guys have thought about it or have any comments. Doug Munger basically says nobody has talked about early frosts and freezes on the I'll say the soils and the relationship from soil freezing and the like to summer ground moisture. And I'm just wondering if this is a question that lurks. I know most of my work is in the Sierra, and this is a question that really lurks there a lot. Is lack of snowfall, lack of early snow means that you get ground freezes where you never would see them in the mountains in those years where the snow takes forever to show up. And that always makes me think, okay, wait a minute. Are we missing a bet here? Because our models typically don't know much about soils that freeze and things like that, at least the ones we tend to apply in our Western mountains. So any thoughts from either of you? Because I just have questions. So,
Yeah, I would say that the reason that we haven't been talking about it is sort of what Mike just said, which is that, yeah, it's not something that we model particularly well. We do know though from, if you look at, there's been a few papers, like I know at CSU, Stephanie Camp has looked at this a little bit, and in some of the predictability work that I've done, what happens in the fall seems to really have a surprisingly large impact in what happens the following year in terms of the condition of the soil. And there's kind of this memory of, a wet fall or a dry fall really has a lot of impact. I can't really say much more than that, other than it's an interesting and a kind of a nice long lead time that could be useful if people harnessed it in a sort of organized way.
Chris, you got any thoughts?
Well, I was just thinking about that same thing earlier, where the deficit of moisture in the fall is an indicator of how much of that snowmelt is going to be taken away and not flow down the hill. So that could be a useful, predictor. Makes sense.
So then just to return to that question that Marty asked earlier, and it's another one of these god-awful questions, not that he's the only one who asked god-awful questions, but just another one that the crew has come up with. And that is, he asks everyone, how might the massive landscape changes underway in the West due to wildfire and beetle kill affect runoff and trends? So we touched on this a little bit ago, the business of as the vegetation changes, how is this all going to play out? But he's being relatively specific about how the vegetation is very likely to change. So any additional thoughts?
Chris, would you like to take this one?
But, a few years ago, I would have said, negative feedbacks are going to just take care of that. It really isn't going to matter. But the more I've looked at things, I'm really beginning to appreciate detail more than I used to. And so therefore, I plead ignorance.
I would just say that my understanding is that when you have, say, there's kind of this cascade of events. Let's say you have dry weather, fire weather. You may have a fire. You may have beetle kill because of the sort of weakened trees. What tends to happen is then the vegetation uses less water, and it almost has like a normalizing effect in terms of you tend to see more runoff when the vegetation is using less runoff or less water. It's really a question of the devil being in the details, right? Which is, I think, what we're alluding to. That is that magnitude going to be significant? I think it will, and I think we have this paper that's in review where we looked at a bunch of basins in the West, and that there is a noticeable like a sign to after a fire that you do get noticeably more runoff. So to the extent that I can make this statement, I would say that it may actually help to counteract things a little bit. Then I apologize for such a general statement there.
Yeah, I'll toss in. I'm trying desperately to pull it up because I don't have the author's name. There's a paper that just very recently was accepted. I saw it on Twitter and all that sort of thing. But basically, there's a new study out. I believe it was Nature Geoscience, but that could be off, by a group that, and I'm not going to be able to pull up the name in the next 30 seconds, but where they looked at this question of thinning of forests and the like and what the impacts would be. And they ended up breaking it out and finding that whole energy limited versus water limited dichotomy makes all the difference in what you end up seeing from a thinning of the forests. So I think that's going to be a topic that dichotomy is going to be a topic that's going to hound us for a long time to come. And earlier I said, and I'll just to wrap it up, earlier I commented when I mentioned this, that I was kind of a skeptic that we really know what happens with changes in vegetation in Western mountains. And my particular gripe isn't so much that, well, we don't actually have a great handle on it as a way to affect the overall runoff and the like. But my big gripe is that I'm not seeing anyone talk about what happens to floods and extremes when you do that. Everyone is paying attention to the long-term yields of these things like they were, a farm or something. And I look at some of these places that have burned off or some of the places that have been cleared out. It's like the flood generation properties of these settings before and after have to be completely different. And so I'm concerned that we're all gaga over the potential resource benefits and ignoring the potential hazards involved. So just to toss that into the mix. Anyway, I believe now we are actually over time. So Nathan, why don't you take it away? And by the way, if you can tell us, or Anna or somebody, there are lots of other questions. What's the plan for dealing with any questions that we didn't get to?
Like, this is great. I wanted to point this out too. There are some excellent questions there in the chat and some more are coming as we wrap up here. So Anna, we'll save these on our side and perhaps send them if it's okay with panelists to each of you, and maybe we can continue some of that dialogue here offline. I just want to thank all attendees for engaging in the way that each of you has here, despite our Zoom format. Chris, Ben, Mike, Angie, of course, has now gracefully departed to teach here. I just want to say thanks to each of you for your presentations today and for this discussion. I'd underline that this session is so very important to this year's dialogue on drought, and it really does uniquely prepare us for day 2 tomorrow. And so I wanted to, just before we break, very quickly show you what's coming there. Bring early your coffee or tea to join us for the first ever student research presentation session. Chris, Ben, Mike, we would love to have some of your students join this session in future YBR years or early career mentees that you're working with. We hope this session will expand in time. For the first morning session, 9, will bring a group that's going to tackle head on that current water management strategy area that you've prepped us so well for here. That will give way to a session at 10 that will get us looking at, importantly, strategies for adaptation and action. So I just wanted to underline how dynamic our day 2 here is after a really productive day 1. Special thanks again to all of our day 1 speakers here before we close. That includes Carrie, Marty, Josh, Megan, Mike, Ben, Angie, and Chris. We look forward to reconvening with all of you tomorrow.
Thank you.
Thanks, Nathan. And thanks, everybody.
Excellent. Take care, everyone. Thanks
Thank
again.
you.